Thanks for the introduction again, and thanks for hosting this series. So today I'm going to just talk a little bit more about the proof. I won't include everything, of course, but I will just try to point out some of the interesting points and also some subtleties. So really in the proof, the noticeably new points are just two. One is the FOP perturbation scheme. The other is the construction of global charts, finite dimensional global charts, all moduli spaces. So, so first, let me tell you how to, more details about this definition of the chain complex. So last time we explained how to construct global smooth Kranich charts on the Floer moduli spaces. So let's assume, suppose we have constructed global A charts for the Floer moduli space at MPQ. So I will also label it with this Floer because we're going to discuss different types of moduli spaces. And part embeddings from the product of two parts into a stratum, co-dimension one stratum of a bigger chart, where if these two Floer moduli spaces are non-empty. So remember that in this Floer case, the domains of those second moduli spaces are will have boundaries and corners in general. So then you can just from the K charts which has compactly grouped symmetry, and you just divide by this group of symmetry, then you obtain this D charts, derived orbifold charts. Then we obtain E plots. Let's call them CPQ, UPQ, EPQ, SPQ, where just divide by the group, and all the construction guarantees that the stabilizers are at most finite. So indeed get some smooth orbifolds with boundaries and corners.
So yeah, so the GPQs are PU V plus 1, where D is the
PU D plus 1, where D is the energy. Yes. But I mean, actually, in the paper, we actually modify this a little bit, so it's not exactly PU D plus 1. It's like some particular subgroup of it. But to guarantee that if you have two such groups, you multiply them together, then there's inclusion into a larger one.
Yeah. So that's kind of what I was searching for.
Okay. and also the corresponding D chart embeddings. D chart embeddings. So now we want to define a chain complex. So we want to perturb those sections and to obtain certain integers. So those integers will be coefficients of the differential map. So then we basically in this whole series, I just ignored how we construct this normal complex structure, but there is a way to construct a coherent system of normal complex structures on all the moduli spaces, as well as orientations. So then we want to perturb those orbifold sections using the FOP perturbation scheme. And naturally, we do some induction. So we inductively So first, if you have a moduli space which has no boundary or corner, then that's just a smooth orbifold. Then you can just use the absolute version of the perturbation theorem. And one again. Choose a strongly transverse, normally complex, a normally polynomial perturbation. Let's say a C0 close to the original section. And let's just do one step of the induction. Suppose we have a moduli space has only codimension 1 boundary with no corners. Suppose UBQ has only dimension 1. Let's say has only one codimension 1 stratum. Say corresponding to the configurations that breaks at an orbit R. So suppose we have chosen SPR prime. It's RQ prime. Which are, like in step 1, they are strongly transverse, normally polynomial section perturbations. Then we want to use the product of these perturbations to generate a perturbation on the boundary. So there is something to talk about here. So consider first the product perturbation. So one important thing for this, also very basic thing to continue this induction step is that if SPR prime and RQ prime are both strongly transverse, then the product is also strongly transverse. So if SPR Q are strongly transverse, so what is the product? This is not so obvious.
No, you have to remind somewhat what strongly transverse.
Yes. Okay. So if you have a normally polynomial type perturbation, then or a section, then from this section you can obtain an associated map into some affine space, and then this associated map should be transversed to some singular variety with respect to a Whitney stratification.
So strongly transverse just means like transverse to that variety that you constructed, the stratified variety on the polynomial space.
Yes.
Yeah.
Yes.
Okay.
So when you take the product, you have to change. Then you have to relate the two varieties to the other one.
Yeah. So suppose you have two algebraic varieties in two different vector spaces. You multiply them together, then the product is a singular variety. And then as a product itself, it has a canonical. For example, it has a canonical Whitney stratification. Whether this Whitney stratification is coming from the product of their own Whitney stratifications or not. It is true actually, but nobody have ever write that down. And in this case, we modify this fact a little bit in incorporating the group actions and the particular variety. I mean the particular variety, the property of this specific variety. So basically, the proof of this lemma boils down to this fact that the product Whitney stratification, the product of canonical Whitney stratifications on algebraic varieties is the canonical Whitney stratification.
Hmm.
Yeah.
This is the multiplicativity property
Yes.
that we were going to do.
Right. So I will not explain how to prove this, but this is something you need to do. So then this lemma shows that if you perturb those two, well, then the product is strongly transverse and will give you the expected, say, for example, countings, you know, so anyways, so that's the first thing to notice. And another thing is that this product of charts is not the same as the boundary of this larger chart. They differ by a thickening, additional thickening. So so to extend from the product to the boundary using use the in fact here's the part of embedding. So actually the chart embedding means in particular that on this product space there is a vector bundle and orbifold vector bundle FPRQ to the product such that the boundary PRQ UPQ is isomorphic, say as a stratified orbifold with boundary corners to a disk bundle in this total space in this bundle F PRQ. So in other words, the product, the boundary is thicker than the product because you include more parameters.
So this bundle mean this is higher dimensional.
There are some, you know, so
this for me is usually two-dimensional.
This what?
For me,
Sorry, ball bundle.
Oh, ball bundle. Okay.
Okay.
And presumably is that a even dimensional?
Yeah. Yeah, it's a complex. Usually.
It's complex. Yeah. So that is where some of this orientation business, some of the conditions maybe at the very beginning.
Yeah. Yeah. This is actually part of the definition of chart embedding. So let me just.
But for the perturbation scheme, it's really important that Bn is a complex.
You can let me.
Because from there you extend it to the inside.
Yeah.
I mean, you add something to the, you look at orientations near the boundary where you start with this and you embed it. Then, if you have something complex, then there's a natural way to extend that.
Right,
so presumably that is.
Yeah, in the construction, it is.
In the construction, it is.
It is indeed complex, but for the perturbation, I mean, if you.
No, for perturbation doesn't matter,
doesn't
but
matter,
at some point your orientations have to.
Yeah, orientations will.
That is,
Right.
I guess, the thing is.
I have another question about coherency with respect to this product.
Mhm.
So the isotropy groups for P, R, and RQ, their product is a subgroup of the isotropy group for PQ. So then if you look at these varieties, Z sub G, the one for the one, so they're on the one hand for the product, you have VG1 cross ZG2.
Yeah.
It has some stratification.
Yeah.
But on the other hand, you have Z sub G, where G1 cross G2 embeds into G.
Yes.
And this is smaller, so this is because
So-
of the larger group.
Yes.
So
So the statement is just that the restriction like the restriction.
yes. So
The
I guess I was wondering, basically, like I was wondering, you have two Whitney stratifications on these G1 and G2. So, I guess you get you can take their product or something and you get one on ZG1 cross G2.
Yes.
And then I was wondering how you get the one on Z to the G. Does this use this like restriction of this functoriality under restriction groups or?
So first is like for if you have two spaces with two different group actions, you take them product, then this product has the action by the product of two groups.
Yeah.
And then if you look at any point and the stabilizer is always be a subgroup times a subgroup. Right. So then you can still for the product space, you can still say stratify it according to the isotropy types, like the stabilizer, which is a subgroup of the first group and a subgroup of another group, and there's there's two or the stratification is indexed by the product of two partially ordered sets, and you just stratum by stratum to compare the product within stratification and the within stratification of the product. You just do it stratum by stratum.
Oh.
And there's a product partial order which allows you to do induction.
Thank you.
So now this we just discuss this phenomenon in a more abstract situation, terminology. So let me introduce the notion of stabilization of the D charts. That's some C. I will omit this footprint map, the A B chart. That's orbifold. Complex bundle. The stabilization of C by F is the D chart. where you just replace the original domain, which is orbifold, by the total space of this vector bundle. And you also add a piece of this vector bundle into the obstruction bundle. And you, for this factor, you use this tautological section of this bundle F. So this is called a stabilization of this original D chart. So in a derived sense, this.
What's the last letter there?
A tautological tau.
Oh, tau. Okay.
Tau stands for.
Okay, no.
Okay. So in the derived sense, this should be identified with the original chart. And the
sorry, can you explain what you mean by that? I never know what people mean.
So it just means like if you want to construct, for example, you want to regularize the moduli space, you just need to add more parameters. That means you add abstraction bundle to. So originally, like d bar u is not surjective. Then you solve d bar u modulo some finite dimensional space. Then, but the finite dimensional space is not canonical. You can just add one. You can just increase the dimension of this extra, additional parameters or the obstruction space to get a different regularization. So if you add one more set of freedom, then you actually you get more solutions. The solution space get the dimension increases. So just means in this abstract terminology means that the chart, the regularized chart becomes thicker. So from a orbifold to a bundle over the orbifold.
Yeah. My question was semi-philosophical. I guess, why do people call this derived?
Derived means you know when you want to consider some singular things, like the so the tangent sheet, for example, is resolved as like h0 h1 up to higher. So then when actually it is not smooth, then you tend to have like more terms to talk about the same thing, as if it is smooth. So for example, if the original moduli space already regular, then you can just choose the obstruction bundle to be trivial, to be the zero bundle. So
yeah, you have a manifold, for example, that's very nice. And the manifold might be solution space of a nice form, what you just said, but sometimes you have to deal with crappy stuff for a long time in order to resolve it. And then you just write down, well, this crappy thing is the zero of some in a good situation, but the section is just bad.
Yeah.
So just to keep stuff going while things are not nice, till at some point to come up with an idea how to resolve all this mess in some way. You feel better now? You feel so better now.
You just treat a singular thing as a smooth thing, modulo some additional, you treat the singular thing as a smooth thing, high dimensional smooth thing together with an equation.
I feel like it's like you want to make manifolds closed under taking kernels, sort of, but they're not, right? Because you can't like smooth unless the map is nice. So
yeah, you get more possibilities to do stuff which you can't do really when you have not transversality and so on.
Yeah.
Just
at least when people talk about this kind of derived thing.
Okay. So then regarding the FOP perturbation scheme and this notion of stabilization, one natural expectation, and also it's not difficult to prove, is that if S is a strong transverse, normally polynomial, section. So is this the reason is very simple because tau f is basically a linear map, order 1 polynomial, degree 1 polynomial. So it's at least it's still polynomial map fiber-wise, and also this linear map is transverse even in the classical sense. So it will just, if you just study the definition of strong transversality, it will imply automatically that this stabilized section is also strong transverse. Okay. So now let me draw the picture. So then from the product of two already chosen perturbations, you can cook up the product perturbation, and then use the fact that near this embedding image, a neighborhood is inside a vector bundle. Then you can use this canonical extension to extend the product perturbation, which is defined over this line, and to a neighborhood. So that is also a strongly transverse normally polynomial perturbation inside the open set of this boundary stratum of this chart. I mean, you can just extend arbitrarily away, because away from this neighborhood, the section is bound, is non-zero, it's non-vanishing because this linear. This is a linear factor. So you can also extend the perturbation to sort of arbitrarily without creating more zeros outside this neighborhood. So this tells you that you can actually extend the product perturbation to a strongly transverse normally polynomial perturbation on this boundary stratum of the new chart you're working on now. So we obtain a strongly transverse normally polynomial perturbation on the boundary stratum. And then we need some Floer structure to extend to the interior. Sort of canonically, then extend into or a little bit into this interior, and then extend it to the pole. And the existence of a strongly transverse partial, normally polynomial perturbation is because this notion of a transversality is still boils down to the classical notion of transversality. So if you have something which is strongly transverse near a closed set, then you can extend this object globally, which is still strongly transverse and without changing its value near this closed set. So this is how we can carry out this induction in the simplest step. That is, you just have one codimension one stratum. So it's just more complicated, and you requires more compatibility conditions to do the general situation where you may have just higher codimensional strata. Okay. Okay. So now we can just define those integers. Perturbations. We define NPQ is an integer to be the count of isolated zeros in the manifold part of this perturbed zero locus. And then those coefficients can be used to define the chain complex. So let me, before I just write more algebraic stuff, let me just draw one more picture to tell you what happened. What's the intuition about this FOP type perturbation? Well, let me draw a part of the You can think this as a neighborhood of a corner, codimension 2 corner inside some thickened moduli space, and while this red region is a fixed point locus of the local symmetry group. So suppose the index is 1 in this case. So then the zero
index is
Fredholm index, yes. Fredholm index for this moduli space is 1. Then you expect the zero locus is a curve. Well, when hitting the boundary, they are just isolated points. So you should expect those away from fixed point locus. You have actually the curves with boundaries. But the FOP perturbation scheme tells you that in the free part, the limit of the free part of the zero locus in the fixed point locus is having codimension 2 or higher. So in this case, those curves will not intersect this red region, will not touch this region. However, in this red region, you don't have the ordinary transversality, so it is very singular here. So that means after you do this perturbation, the actual zero locus look like something nice away in this index 1, or less case, you have something nice here, which is just as good as the semi-positive case, for example.
So index 1 here would be corresponding to Mach index difference 2.
Yes. Yeah. But that doesn't mean there are no other zeros. But in this region, you have just more singular things. But then you don't consider their contribution anymore.
Wait, so why is it Morse index 2? You're saying because we're thinking about family
divided by R out in the first theory.
Oh, okay. Well, but just okay, and also because we're thinking about families of like if we do the homotopy, then
so the homotopy is here if you divide it by R, one dimension,
okay.
So they don't hit this best.
Sure. Yeah.
So then,
But you said that I don't know, maybe in your first talk that one can also study non-free things.
Yes.
So one can prescribe the group.
Yeah. Yeah.
And then one can, knowing this, resolve this, but for other groups it might be messy as well, or something. Is that how it works?
For defining invariance, yes. For the chain complex, I don't know. I haven't seen if the things, for example, we want to study things happening here, whether the outside things will affect. It's not so clear. I haven't thought about that.
And can one expect interesting invariance coming from there?
You could have like a family of Floer homologies parameterized by those symmetry, the isotropy types. Okay. But then those the index will not be the same. Like they are actually the isotropic group. So the index is actually an isotropic group, which is finite group, together with a pair of complex representations, which describe the normal behavior of the moduli species. So they may have a different type of Frankel index. So let me just now introduce this moduli. This is just the form of the ring of Laurent series with integer coefficients. So because here the energy are always integers, and we can just use integer exponents. So then the rest of the definition will be just writing down things which have been already done many years ago in the same way. So we can define a chain complex. We have of the MZ modules generated by tapped periodic orbits, and graded by mod 2n Conway-Zender indices with differential used from the integers. Okay, so then this tells you there is a homology group. See. So then we need to compare this with the ordinary homology of the symplectic manifold. So then we use this EXS construction. So we choose a Morse function on the manifold and the remaining metric, satisfying the Morse-Smale condition. And then we can define the Morse complex And more generally, we can define the so-called Morse flow category. Basically consisting of a bunch of moduli spaces. Of possibly broken trajectories. Any pair of critical points, you have a moduli space of smooth or broken trajectories. So we want this. Those are naturally smooth manifolds with boundaries and corners. So you may need to impose a little bit more conditions to guarantee the gluing. It's nice. So for example, you can require that near critical points F and G are standard quadratic functions and Euclidean metric.
But you have to do things are not naturally manifolds with boundary and corner.
This is not. I think
no, no, you have to say certain things because how it goes. I mean, no, I think you have to make some choices.
You make some choices.
Yes, you have to make.
Yeah.
There's not a. I think I couldn't give a talk about this now, but so for example, when you choose a gluing profiling and glue things together, then that determines what it is. And there were at some point people said, well, we look at the level sets and make a construction, but that doesn't need to manifold with boundary and corners. And the problem is that trajectories might go with different speeds to the critical points. And then that causes some problems. You might actually have cusp ends. I think Morphka maybe at some point wrote something about
You mean like it's a non-Morse function? Non-degenerate?
No, the thing is, whatever, when you have F and G, whatever natural data you have there, I think could lead. And people said, well, we know we take level sets in the critical point here, and then we cook something out of this, and then it gives a manifold, naturally manifold with boundary corners. And I think Morphka wrote something about this. It's a long time ago. In part of something that you can actually then get things which have cusp. So the corner looks like a cusp. And that has something to do with the different speeds, how the flow lines actually approximate that critical point. Yeah?
Wait, so what is the
eigenvalues? So in certain situations that will happen. So
what is the question? So the question is whether or not this has a natural.
He said he has a natural smooth structure with boundaries.
Hessian has different eigenvalues, right?
When the Hessian has different eigenvalues, there are possible problems.
Okay, but what I mean, like, let's assume it's just a standard quadratic function.
Well,
with a,
so
in that case.
So well, now if you assume that your Morse function has certain properties. And the G has certain properties, then it's possibly managed. But you have to say something. I think.
It's not for any Morse milk.
No.
It's a paper by Wernham which assume this condition, like the near critical points, everything standard. Then
presumably you have to have the critical points the same, the eigenvalues the same, and blah blah blah. So I don't know. So I could imagine that, but I think one has to say this.
When you're happy, but you're happy doing that here, right? Because it's just because you just want to find some.
Yeah, we don't need to.
No, it doesn't matter in his case what he takes. So, but anyway, so I think if you just don't say it, that there have to be special choices made and give a reference, then some people might raise a red flag. I mean, you have to do it. So you have to look precisely what it means, but I think you can arrange that.
Okay, so then we consider this moduli space of spiked disks. is stable. X to Q, X to P, which means configurations like this. And so this is a combination of a half gradient flow line and connected with some homomorphic curve perturbed by this Hamiltonian. So let me write down this equation here. So this is relevant because this affects how you choose the equation, or some data affects your construction of the global charts. So here, on the two-dimensional components, the equation is it's the homomorphic curve equation perturbed by this Hamiltonian field, Hamiltonian vector field parameterized by two parameters, S and T, where S is in R is S1. So HST is an interpolation from a constant function to your Hamiltonian. And you have a freedom of choosing this constant function because adding a constant doesn't really change the Hamiltonian vector field. So that in particular, near the left end, the Hamiltonian vector field is 0. So near here, it is a holomorphic curve, actual J holomorphic curve, and near the right side, it's a equation, it's a Floer equation. So let me just say some general nonsense. So those moduli spaces let's modulize be packaged into a flow by module from the Morse.
What? Oh, flow. Oh, flow.
Flow by module. Flow categories. So in particular, there are two kinds of structure maps in this flow by module. Structure maps corresponding to either a configuration can break on the left, creating a broken Morse trajectory, or break on the right, creating a Floer trajectory. And some compatibility conditions, like associativity conditions for those structure maps. So now on the Morse part, the moduli space are already regular, so there's no perturbation you need to do. And on the Floer part, you have constructed the system perturbations. then what you want to do is to create, to construct global derived orbital charts on the PSS moduli spaces, which extend all the existing charts, and also inductively choose perturbations which extend the existing perturbations. So then after that, we just want to define integer contents. XP, PSS, and define the temma. So PSS, CM. Let me be a little bit loose about the grading, because actually the Morse, the gradings are, you have to do some shifting and the reversing of the grading to match the gradings of the complexes.
Reversing, you mean what? With a minus sign?
Minus sign in the half dimension. Yeah.
Yeah, so it's always.
Yeah. Okay. So there are a few things that are different from the case of Floer moduli spaces. I want to just talk about two things here. So the first thing is that the energy. So remember that we use the integrality of the energy in the global chart construction for Floer moduli spaces. But here for the PSS moduli space, the energy is not necessarily a topological number. So if you, let me just write down the formula, which might contain a sign error. So for the energy of a PSS factory, U is which, because of this, there is a derivative, the time derivative of the variation of the Hamiltonian. This guy is not a topological number, so not necessarily an integer. So in order to get a similar construction, we just use a different notion of energy, which is integration of a non-negative form. That is why we don't interpolate between the Hamiltonian and zero, but interpolate between the Hamiltonian with a constant, which is either very large or very positive or very negative, to ensure that this term has a definite sign. So if this term has a definite sign and this is positive, so that can guarantee that this topological, this integration is actually a the whole two form is the energy density, so this is non-negative, and if you guarantee the definite sign of this term, then that will imply a definite sign of this term, and the integration of this two form is topological. So we just use, and this is also integer if you choose C to be integer. So we just use this form whose integration is an integer over the domain.
So you can't do it without PSS by just taking an autonomous small Hamiltonian?
It's possible, but we just think this is.
So you tried this, or you
haven't tried hard enough to.
But you tried.
Yeah. There is like the localization,
sort of
this, like S1 equivalent.
Yeah. So in some sense, in certain cases, we can show a solution would be actually a gradient flow line, and this would be. But here, of course, with this, it's presumably not even true.
Yeah. So, anyways, so you have this in the integration of this two form is is an integer and is also everywhere non-negative, as in the Floer case, then you just use this two form to cook up the line bundle over the domain and to use the notion of use frame curves to construct the thickening of the moduli space. So this is one difference from the previous case. Another difference is that we need to use this auxiliary moduli space of stable maps into the projective space, which carries a canonical smooth structure because it's a part of it is a smooth algebraic variety. So in the Floer case and also in the in the PSS case, we need to use a different moduli space into the projective space. So in the Floer case, we use the auxiliary moduli. Which is the moduli space of stable cylinders into CPD. Which means that so every representative is still a stable map into CPD with two mark points. But if you have two mark points, one is input, the other is output, then between them there are a bunch of cylindrical domains, cylindrical components. And then when you define the equivalence relation, on the cylindrical components, you only consider the reparameterizations by the translation in the time direction. So then in here there is a open set which is all those cylinders whose images are not containing any hyperplane, and that is a smooth manifold with boundaries and corners. Very easy. It's a smooth manifold with boundaries and the corners. And also for PSS case, you have a similar one. That's which is roughly those kind of configurations. Where the domain has a distinguished component, which is identified with the region where you do this interpolation of Hamiltonian functions. And to the left, you have just holomorphic spheres, and you can reparameterize in any possible way. And to the right, which are supposed to be the domain of Floer cylinders, you only reparameterize by the time translation. So there is also corresponding moduli space of this type, and there is an open subset which is also a smooth manifold with boundaries and corners. So you use those auxiliary moduli spaces to as part of the smoothing procedure.
And you need to show that the embeddings that you get from your framings land in this.
Yes, the frame is just because if it's a frame, then the induced map is automatically not in any hyperplane.
Yeah.
And so basically there are a few other differences in between the PSS and the Floer case, but I will not talk about them now. So, but in short, we can construct details C and P SS for modulus PSS modular space with part embeddings. Two kinds of part embeddings. Morse cross. And then the way to perturb the sections for those PSS charts will be just exactly similar, identical even to the Floer case. That you have the boundary, you have the boundary perturbation coming from product of existing perturbations and the stabilization, and then you extend using the collar structure a little bit to the interior and then extend to the whole chart. So then by perturbation, PSS parts, that extends. Or charts. One of 10 counings. So then the rest of the proof is that we reverse this PSS. We obtain something called SSP by just reversing the interpolation. You interpolate from Hamiltonian to another a large constant with a large integer, and which is similarly 1/10 another impact of SSP. So ideally, you prove that they are inverses to each other in homology, but you don't have to do that completely in order to prove the Arnold conjecture. So this is also a strategy of the proof of Filippenko and Warham using polyfolds, proving the rational version of the Floer homology. You don't really need to show that Floer homology is identical to the Morse homology. So basically, what we want to prove is that the composition of the two maps is the identity of the Morse complex plus higher order term.
So you think there are some more inverse to each other? Not really.
I mean, over Q they are, right? They should be.
Yeah, but
So,
what do you think?
I think they should be, yeah. Okay. So then the strategy also standard. You just geometrically compose these two type of equations. That's and you realize this concatenation as the boundary, as one type of boundary component of a larger moduli space, where you can glue them together. And then you turn off the Hamiltonian perturbation. So then to actually prove this proposition, you need to also cook up. You need to consider this kind of moduli space, which we call the homotopy moduli space, and you need to put global charts on those moduli spaces, which extend all the existing charts. Okay. So on this boundary, which you can think this kind of configuration, the moduli spaces of this kind of configuration defines a flow by module from the Morse flow category to itself. And then you do the FOP perturbation for this system of moduli spaces, you get countings, and that induces a chain map. And that chain map is filtered by the energy. And if the energy is zero, these are really just counting these constant trajectories, which gives you the identity part. And with energy is bigger than zero, you have this higher order terms. And the counting of this whole moduli of this moduli space tells you that there is a chain homotopy between this chain map and this chain map. I will say in homology. So that means homology SSP for this PSS is invertible. Twice PSS. And both sides are finitely generated modules over the PID lambda c. And then you can just compare their and then grade it by z. And then you can invariant factors to derive this version of Arnold. Okay. I think that's it. Yes.
Thank you for your heroic act.
Yeah, this is a lot of time. A lot of time.
So, yeah, but what do you think about the Lusternik-Schneermans here? Because now you have this more refined view of what's happening.
Yeah.
And perhaps, I mean, maybe I told you the story that Floer in 1986 thought that it should not, it should not be true in the sense as, I mean, even on a homological sense, as so Arnold has this picture with what smooth maps do. Yeah, that's presumably not good. But you can have an associated homological picture, and then you have Lusternik-Schneermann estimating cup products. Of course, nobody ever got there. I mean, if you have holomorphic spheres and so on, then it wasn't so clear. So there's some results by Schwarz, I think, under the strong assumptions of omega vanishes on pi2 and this kind of stuff. But so Floer thought that he believes that the Arnold conjectures, even in that sense, are not true in general. And
the
then,
Lusternik, like the cup product bound, he doesn't think that was really interesting.
So and then he said he felt that it was above his pay grade, and one should get Dusa McDuff excited about the question, which never happened.
Yeah.
So because he saw Dusa as a person who would be able to come up with a counterexample. But
I see. To come up with something that's not.
Yes.
That makes
so
sense.
he thought that was his plan of finding a counterexample. Let Dusa do it. So. But
maybe the correct thing.
It did happen. But now one has a much better picture here, much clearer about what's going on. And Floer's original proof of the Lusternik-Schneermann theory, but under this additional assumptions, was doing Floer homology first and then making some other construction and getting the Lusternik-Schneermann theory out under his much stronger assumption. So I had a different approach, and it shortcutted Floer homology. But anyway, so here now you have a very precise picture about the Morse theory, and then you can meditate about it. Where should the Lusternik-Schneermann theory come from? And so maybe then one can see here where the gap. I mean, if Floer was right, maybe see where the problem would be, and then maybe one can cook up an example.
So is the Lusternik-Schneermann thing? Is it so like? It's known, you're saying, in the case where for maybe the rational, or maybe over the integers when. So
if omega, say omega vanishes on pi2, then you can do that. Now, when spheres come, they mess up sort of. Then you might use. So then under certain say monotonicities, maybe they have a quantum cup product or something. But but that's in general weaker, I think.
Isn't there just some like spectral kind of invariant argument for this solution? I mean, Saban Sifadini explained this to me at some point, that it's like there's a pretty slick kind of spectral invariant argument. You take like that the cup product sort of increases the spectral invariance or something like that, and then like you can use this to say like like in the cases where it doesn't, then you actually know something about the cases where you sort of degenerate. Like if you take one of these cup sequences and the spectral invariant doesn't increase in one of the steps, then you know something about then you can conclude that there's like infinitely many.
But that's standard in Lusternik-Schneermann theory. So in standard Lusternik-Schneermann theory,
maybe it's the standard argument. It's just more theory.
Characterizations, and if two characterizations are the same, then the set of critical points has some infinite size in some sense. But here the question is, the problem isn't really variational. The problem is multi-valued variational, because you can go, because of omega, you have a multi-valued. Therefore you take the equivalence relation that you look at the same disks with the same omega to make it. So in some sense, you go to some covering of the loop space to make it variational.
What is the multi-value? What are you saying?
No, if you integrate omega over a disk, then if you take a different disk, you get a different value. So therefore, he said we introduce equivalence classes. But this technically means he is in the loop space and he goes to some covering on the loop space on which this the one form becomes actually exact. That is what you do. And this kind of stuff seems to interfere possibly with having Lusternik-Schneermann. So it must come from there. But now if you have much better machinery now and so on, that maybe it's worthwhile to have a look at this. Because you guys are on the roll now, maybe just finish it off. Because then we have a complete story. So So the original Arnold picture is presumably too naive because of in low dimensions, bad things can happen between critical points and homology and so on.
Mm-hmm.
And so I think everybody would be happy if we have things over the integers and we could say Lustenau-Schnirrmann theory is correct or is not correct. Yeah?
Mm-hmm.
And then we can write a book about it and forget about it.
Yeah. Move on to other things.
So it might be worthwhile to have a look there. So I think your presume is the closest now to this kind of question. So, and I think that would be a big thing also.
Mm-hmm.
Okay,
Right. Cool.
cool.
Thanks
Thanks
again.
again. Yeah, that's good.
Thank you.